So today we will discuss about topology. So basically topology is study of open sets. But what do we mean by open set in general? So we will define open set with something called axioms of topology. But I think it would be wiser to study a specific subfield of topology, and that is metric space topology, and that will help us generalize the definition of topology in a general sense. So first we will define what we mean by a metric space. So let X be a set, then a function D that goes from X to X to R that follows the following properties: that distance of X comma Y is always greater than or equal to 0 for all X and Y belongs to X, and it is 0 if and only if X equals Y. The second property is that the distance between X and Y is equal to the distance between Y and X. This is the symmetry property. And the third property is the triangle inequality, that X comma Y plus d of Y comma Z would be greater than or equal to d of X comma Z for all X comma Y comma Z belongs to X. So what is this function? So basically what this function says is that we have defined a notion of distance on our set. So these three are the most necessary and basic condition that we will want this distance function to satisfy. So the first one says that distance should be non-negative, and it should be 0 if and only if we are on that point. And the second condition says that the distance between 2 points should be same if I'm even if I'm measuring from x to y or y to x. And the third one is basically the triangle inequality that we will want our distance function to have. So this is what we mean by a metric. And an ordered pair x comma d is called a metric space. So metric space is basically a set that has a metric defined on it. So what are some examples of a metric space? So now we will look out for some examples. So first example includes say R. So say if you have R, then distance would be same as the distance of x and y is equal to the modulus of x minus y. So note that modulus of x minus y is always greater than or equal to 0, and if mod of x minus y equals 0, that would be if and only if x is equal to y. And mod of x comma y is equal to mod of y comma x, and we know that triangle inequality is present here. So R with a usual norm is a metric space. And our second example would be say V is an n-dimensional vector space. Then how do we define a metric on it? So basically we would say that d of u comma v is equal to the square root of inner product of this. I think I should have put an, instead of vector space, say inner product space. But it doesn't matter. I mean, every space can be made into inner product space. So yeah, that was just for completeness. So these were some trivial examples. So now we'll look at a weird metric that we might not have seen a priori. So say x is an arbitrary set, and you define d such that d of x comma y is equal to 0 if x equals y, and d x comma y equals 1 otherwise. So note that this metric is called 0 1 metric, and it satisfies every uh, requirement for a metric that we have asked for. So this is a metric, but this is a really non-trivial metric, and what I mean by that is we have not seen it. I think we have not seen it before. Yeah. So what this means is, suppose if you have your set x, this, and you have a point here, then basically what we mean is there is a neighborhood around this point that contains just this point, and there is another neighborhood that contains every other collection, say x minus x. This is present over here at the distance 1, and yeah, basically what we mean is x and x comma the element x are well separated. So this is what we mean by a 0 1 metric. So now we can do many things with a metric space. We can define sequences, we can define what we mean by continuity, but we won't go there since this is that would be analysis, but here we are interested in topology. So what topology is that it is study of open sets. So what we will be interested in are the open sets. So what do we mean by open set in a metric space? So now we will define that. So if x comma d is a metric space, then a subset A of x is open if for every alpha belongs to x there exists, how do I put it, an open ball of x of radius r such that this ball is contained in A and x belongs to this ball. So now you might ask, what the fuck is this ball? So I'm sorry, I haven't defined what I mean by an open ball. So open ball is basically this set. If I say open ball of radius r at x, this is basically the set which is this. So suppose if you have a set x like this and the point x here, then open ball would be just a sphere here in Rn, or say in n or R2, and you have a point here, say x comma y, then an open ball would just be a circle of radius epsilon or whatever you want. So a set is open if it has an open ball that contains the element and belongs to that A, and if it is true for every alpha belongs to x, then your set is open. I think I should write x here, that would be more appropriate. Yeah. So now we have defined what we mean by open sets. Now we are in a good position to study topology. So now we will construct some topological quantities, but I think it should be nice to motivate them or discuss why do we care about them. So first we will discuss about compactness. So first we will discuss about a question. So say we have a function from R to R and it has a domain D, uh, not from R to R but from a domain D to R, and D is a subset of R. And this function is continuous. So what are the conditions on D that are sufficient for the boundedness theorem? And what is boundedness theorem? It basically says that in a compact domain a function is bounded. So we want a domain which captures this theorem. So what are the candidates for compactness? So basically the theorem states that the theorem is that a function from D to R where D is compact. Note that I have not defined what I mean by compact here. Is compact and continuous and it is bounded. So now we want this theorem to be true, and we are finding the candidates of what the compactness can mean here. So first candidate can be, say, a set is compact if it is closed. But if that was true, then note that first of all phi is open, okay, and so is x. So basically this is an exercise. So say if x comma d is a metric space, then prove that x, a subset of x, is open. So, and since x is open, you can consider this function. And is this defined on a closed set? Yes. Is this defined on okay, I think I have forgot to write. A set A of x is closed if x minus a is open. So yeah, since uh, I think I should include this as an exercise to that prove that phi is open, and that would mean that x is closed too. So we have constructed a function that is defined in a closed domain that is continuous but that is not bounded. So compactness cannot be same as closedness. So can we define compactness as boundedness? So say if your domain is bounded, say if it is something like minus pi by 2 to plus pi by 2, then can we ensure that a continuous function on this domain would be bounded? We cannot, because consider this function 10x. It is continuous but it is not bounded. So we need something stronger than both for compactness. And basically in Rn, by compactness we mean that a set X is compact if it is closed and bounded. And I think I have not defined what I mean by bounded. So a subset A of X is called bounded if there exists a real number m such that d of x comma y is less than n for all x and y belong to A. So basically this is the same notion of the boundedness that we have in R and that we have just generalized in metric space. So say if we have metric space X and a subset A, so if you can find a number m that such that it is greater than the distance of any points in the set A, then the set A is called bounded. But even that is not sufficient for our cause for compactness. So the theorem is X is compact if it is closed and bounded. So yeah, I think that should be motivating enough. But the thing that is not trivial is the way we will define compactness now. So definition, set X is, I don't think I should call this a set X. And by the way, if you hear any noise or background hiss, please forgive me. This is like my eighth try or something, but this mic is stupidly not working and I don't know how to fix it, so please bear with me. I think my explanation is not that great either. I don't know why you are here till now, but thanks. So, say A, uh, suppose X is a metric space. So, if X is a metric space and X is called compact if for every open cover of X there exists a finite subcover. Now please don't curse at me, I will explain what this definition means. So first we will discuss what we mean by an open cover. So say X is a metric space, then an open cover of X is basically the collection of open sets that cover X. So open cover is collection uh, such that An belongs to where J is an index set and with a property that n belongs to J, the union is a subset of X. So yeah, basically the collection of all open sets that cover X, and basically a subcover would be say if this collection is funny A and a subset of this collection say funny A star that also covers X. By covers I mean its union is contains X as a subset covers X, then funny A hat, it's not hat right, it's dashed, yeah. So yeah, since I said it dash, so did I say hat or dash? Oh, who cares? Is called mm, a subcover. So yeah, I think we can all know what a finite subcover is since now we know what a subcover is. So now I think we are well versed with the definition of compactness. So say a set X is compact if for every open cover we have a finite subcover. So say if you have an arbitrary open cover, you can always find finitely many open sets from that open cover that will cover your set X. So say you have an arbitrary set X and its subset A. Now suppose if I give you any arbitrary open cover like this, note that since I am a human being, I will not be able to draw infinitely many neighborhoods. So this is finitely many, but I think you can assume that these are infinitely many neighborhoods. And if you can think that, you can also think that you can also see that I can always choose finitely many sets of this kind and cover my set X. This is not a theorem, this is a definition. If I can do this, then my set A would be compact. And now I will claim a theorem that I will not prove because it's a really long proof, and mostly because I don't remember the proof exactly. So if X is Rn with the usual vector space wala norm, then a subset A of Rn is compact if and only it is closed and bounded. So this is the famous Heine-Borel theorem. So it just means that in the specific case of Rn, you can forget the abstract definition of compactness, that is the definition using open covers and finite subcovers. If I say in Rn that a set is closed and bounded, that means that it is compact. But in general metric spaces, compactness is a stronger condition than closeness and boundedness combined. So that is something you should ponder about, and I won't go deep into. So in the end, we can all see that compactness is just defined using the openness of our sets, and hence it is called a topological quantity. Compactness is a topological quantity. So if we are done with compactness, now we will go into connectedness. So what is the motivation to study connectedness? So as we studied boundedness theorem, there is a similar theorem in analysis, a much more important theorem indeed, not a definition, it's a theorem, and that is called intermediate value theorem. That just says if a function that goes from say d to r, where d is a subset of r, that is continuous, then if d is connected, then not then, we'll also add some more hypotheses that say f of a is alpha and f of b is beta. Then if suppose that alpha is less than beta, because why not, then if c is between these two, then there exists a say gamma belong to d, such that f of gamma equals say. This is basically the intermediate value theorem that I think you should have studied already. So here the thing that is not clear is that what is connectedness. So basically a set X, you can have these two, right? I mean, say openness 0 comma 1 and 2 comma 4. So to say this and this. So note that since the domain is open, this function is continuous, but this is bullshit, right? I mean, this function is not continuous. So to remove this kind of pathological arguments, I mean, this is not even pathological, this is just stupid. So we will just focus our attention on connected sets. So yeah, this motivates us to define connectedness. So definition: a metric space X is called connected if uh, there does not exist two disjoint subsets, say U and V, that are subset of X, such that U and V are phi and U union V is X. So these are open, by the way. So yeah, this is what we mean by connectedness. So let's look at some examples. Say if you have a set X, that is, then you can have U as 0 comma 1 and V as 2 comma 4. These are disjoint and the union of this goes to your set X. But if you have something like, say, you cannot have the following thing, it does not exist, and it would be a nice exercise to prove that why. So exercise would be that prove that the certain sets does not exist. And as you may have seen already, the connectedness is also a property purely generated by the openness of our space. So the connectedness is also a topological quantity. And if I have not said it already, topological quantity is just a quantity that just depends on the openness of our space. But yeah, I think that should be enough for a metric space topology, and from next on we will discuss point set topology.